Okay, hello everyone. Hello again to those who are attending online. So we are starting this afternoon with the presentation of Júlio Hoffimann called GeoTables.gl, a universal representation of geospatial data. Thank you.
Thank you, Virginia. So hi everyone, welcome after lunch, right? So I'll try to do the same as Ingrid here. I'll be walking around. I think it's better and more interactive. I will be just coming back to move forward the slides because we don't have a pointer, right? But what's this presentation about here? What the goal of this talk is, I want to introduce to some of you who never seen Julia before, very basics of how do you load with one particular ecosystem geospatial data and how do you manage and process and visualize this kind of data sets, right? The idea here is that you want to merge different representations that you're probably used to from Python, R, which are, maybe you've heard the names like vector data, raster data, mesh data, all these different data sets, they will be loaded in the same representation that you'll be able to then process and visualize with easy, few lines of code. So this is what we call the GeoTables.gl. But let's go step by step building the motivation for this, right? So what is the motivation behind this work, this package? Geospatial data is everywhere. We know how many different formats are out there for you that are used to this: GeoJSON, shapefiles, TIFF, all kinds of different file formats, and it's always a lot of time you spend doing loading and saving of this, restructuring your code to support different formats, changing data structure to just get your job done, right? So it's a lot of time you waste, or spend at least, doing I/O, which is input-output of geospatial data. And it's usually like very painful, right? Like the scientific questions are not about how you load the data, it's basically much more high level. And so the main motivation we had was basically, we're seeing that we've been wasting so much time rewriting code to support different formats, right? So you have different formats, vector, raster data, you have a separate script or a separate function to do this. And it's always like a lot of time wasted or spent trying to support these different representations. So how much time do you actually think is used with loading and saving geospatial data in your workflow today? Do you think it's like 50% of your time, 80% more? How much time do you think it's like loading or saving data? Any guess? Yeah.
When it's done, it's done.
When it's done, it's done, right? So say you have a script that works with raster data, for those of you who know, right? How much time do you think you waste rewriting the script to support vector data or to support any other geospatial data representation? Is it something that you can do quickly?
No.
Right? It's so painful, right? So that's one of the things that we really want to try to address here. So imagine if you could instead like load raster, vector, mesh data, any complex 3D data set from dynamical systems, from PDE solving. So you have climatology, climate models, geophysics models. These are complicated 3D models, for example, of unstructured meshes. You have these solvers that are running, generating these results on geospatial data structures. And imagine that you could load every single data set with a single command line, right? So that's the idea here. Also imagine that you could visualize all these things with the same command, right? So usually when you start working with data like this, you have to have a function to load the specific format, you have a function to visualize that specific structure, and you have to duplicate your code or like many branches to handle these things, right? So what if you could do these things with the same function, right? So we saw this need, right, like for universal representation. I think many people have seen this before, so we just put the energy and work on that direction, which is a need for a universal representation. Of course, there is one thing that I would like to point out in this slide. There's the fallacy. I like it. I call it the fallacy because you see a lot of people saying like no single representation meets all requirements, right? And that's true, but in practice, a good representation can meet 99% of your requirements, right? So if you're working with a representation that really was designed for say, PDE solving, so you have fast access in a given dimension of your data set. So you have an array, and your array has like a dimension that's tightly together. For example, the dimension of coordinates, the dimension of samples, the dimension of time. Sometimes we restructure data so that it has better locality for fast access, but that's an intermediate representation that's used internally in your code, right? So if we could manage to actually have a layer of abstraction that's universal, you could interact with different ecosystems, and when the time comes, you can convert to your intermediate representation internally, do your PDE solving, do your work, and come back and output the same representation. That will increase, for example, the interoperability between different ecosystems, and people can work with different ecosystems more easily. So in order to get to a good representation, we need a good definition, right? So I think in order to get to this point of actually finding out what's the appropriate data structure, we need to ask the question, what is geospatial data? And I will ask this one for you too. So what do you think is geospatial data?
Just whatever you...
Oh,
because of people online.
Sorry. So what do you think is geospatial data? If you had to just give a definition now, anyone can just say a few words like, what is geospatial data for you? Is it an example of a specific data set that you load, satellite image? Is it, how do you define?
Any type of data that has a geographical component.
A graphical component.
Graphical, like a location.
What? Geographical component. Yeah, perfect, perfect. A location. That sounds perfect. Yeah, that's one very good definition. Let me get back here. So what about if we generalize this location to something else? What that could be? Like instead of a set of coordinates, what else could that measurement be assigned to? Is it too abstract a question? Like, so you can assign a measurement to a point, or you can assign it to something else, which is, what is it? What is it? A polygon, for example. So you, in general, you don't only assign a measurement to a coordinate, to a point, you assign it to a geometry, to a volume. So we call this the support of the measurement, right? So in geostatistics, there's this term, it's called the support of the measurement, where your measurement is made. Usually in the real world, in physical world, you make a measurement of a volume. You don't make a measurement of something that is a point, right? Like, so in reality, any measurement you make is a volume. It has like, even if it's tiny micrometers or something like this, it's a volume. So if we can brainstorm a better definition of geospatial data, we can think of examples, as I mentioned, right? So if you work mostly with raster and vector data, you have an idea of what this data contain. What some of you already say, like polygons, points, right? In the case of raster data, do you know what these geometries are? What are the geometries associated with a raster data set? Instead of being a point, a polygon. So that's the point, right? So
that also depends on the raster, right? It could also just be a distance from a sensor.
Okay, that could be a representation, yes. But the measurement itself is associated to something, to cells, right? And these cells are another kind of geometry, just a quadrangle, an hexahedron. So this is a grid, right? So even though you can represent these grids, these blocks, to reference to another distance to a reference point, the measurements are, of course, are associated with these blocks, these cells, right? And if you go to other formats, they're not basically in they are as well in the GIS community, but they're mostly used in the physics community. The people that do physical simulation, they always handle VTK and PLY formats. These are formats for unstructured meshes. We'll cover some of these examples later. But basically, these formats here, VTK and PLY, differently than GRIB and NetCDF for raster, and different than shapefile and GeoJSON for vector, they also store connectivity information. We will see what this is in a few slides, but basically you can represent very complicated volumes with very amorphous shapes, and they will be still connected. You know where the vertices are, what the faces are, and you can connect all these things into a cohesive data structure. So for example, if you want to represent the skull of this animal here, or an helicopter, or the Beethoven statue, you wouldn't use a raster, a grid, or you wouldn't use a shapefile or a GeoJSON file, because these are defined for specific geometries, right? So for a mesh that's more complicated geometry, you need a different data structure. So how to connect all these words into a single representation, we need the definition, right? So the definition here is geospatial data, as I'm saying here, is the combination of two main components. A table of attributes, which is usually the measurements you make on each of these geometries, and a geospatial domain. So think of the example I gave before here. You can think that the helicopter model, this geometry here, is your geospatial domain. It's something that you are referencing in space. It's like a domain. And you can break this helicopter into small pieces, triangles, quadrangles, different smaller geometries. And for each of these triangles, you can assign measurements. So you have the domain and the table, right? So the domain is the representation of your physical space, and the table is how you break these physical spaces into small pieces and assign measurements to each of these pieces. So the table has a set of rows. Each of the rows of the table has measurements of different variables for that specific geometry. Is it clear, or is it something too high level still? Does everyone understand? Can I move on? So just raise your hand if something is not clear, because we'll be building on this basic concepts forward. So tables in Julia, right? So in Julia, there are many different table types. And the way that they got formalized is in a package called tables.jl. Tables.jl is not a specific implementation of a table. For example, if you come from Python, you are used to pandas. If you come from R has a different name, data frame. They have I think it's built-in R nowadays, the data frame. And in Julia, you have many different options. All these options, they communicate between themselves with this abstract concept of tables.jl. Tables.jl is just a way of representing tabular data structures, and they basically mean you have rows, which are measurements. For example, I have here 5 samples, right? So 5 different people. You have variables as columns, right? So anything that you can think that can be structured into this concept of measurements for different variables is a table, right? So you can just formalize this into different representations. So Julia has different representations for tables. For example, the dataframes.jl package that Iga presented is one. There is csv.jl is a different package that has a different table representation on disk. So you can say csv.file and you give the file name, it will be a table. So it will just understand that that file on disk is a table. There's also different tables that are more, let's say, advanced for people that come from computer science databases. So you have databases that also implement the tables interface. And so you can access SQL databases or NoSQL databases. All these databases used in computer science can also be interpreted as tables. And so the package tables.jl by Quinn was the one that formalized all these high-level abstractions. And as I mentioned, like Julia comes with built-in tables and non-built-in tables. The built-in tables here are 2. So if you install Julia in your machine, you have 2 ways of representing tables without needing any package. The one is a named tuple of vectors. If you see here at the bottom, that's one example. So how do you create a named tuple in Julia? You just put parentheses, right? And you say, my first column is the column name, which has these values here. You put these values into a column vector. The second column is age, and I put the integer values here as a column, and so on and so forth. So this is the first built-in representation. So if you type this in Julia, you get a named tuple of vectors, and that is a table. So you can make sure that if you check the tables.jl package and ask if this satisfies the tables interface, it will. The second representation is the vector of named tuples, right? So if you go one slide more, you see here that you have, instead of focusing on the columns, right, you focus on the rows. So here I'm creating a vector, so I open brackets and I close brackets, and each of these entries here is a named tuple. So here, instead of constructing a collection of colors, I'm constructing a collection of rows. And if you follow this pattern here of a vector of named tuples, Julia will also, tables.jl will also understand that this satisfies the table interface, right? So what's the difference between these 2 built-in representations? Basically, When you construct a column-based representation, it's most of the time you do this because you're operating on a whole set of measurements for that geospatial domain. And you usually do operations more often in column measure orientation. But sometimes you want this row measure orientation, especially when you're dealing with streams of data that are possibly infinite, right? So if you are building an API or software that consumes infinite length streams of data, for example, IoT, you go for a row measure representation because it can have infinite length and you can consume this table row by row instead of having to materialize full columns of data. So what are other types of data? I mentioned already. So there is dataframes.jl, which is a very mature package. It's been there in Julia for a while now. It has top-notch performance. It's very well maintained. And you can see here that the syntax is pretty similar to the column-based representation that comes between with Julia. The only difference is that you add this constructor here at the front, right? So you have the same parentheses, opening and closing, but you put a data frame in before and then becomes a data frame. What are the benefits for the data frame? It supports additional syntax. So if you create a data frame, you can access subsets of rows, subsets of columns with very convenient syntax like you do in pandas or any other table from other languages. It's very good for data science, and I think it's the go-to package for people doing data science and manipulation. Other examples, as I mentioned, so if you think of CSV, you have the csv.jl package that loads a file as a table. You have the XLSX package that loads Excel spreadsheets as table. So if you work with this format here, XLSX.worksheet, that will also implement the tables interface. So you can directly load an Excel file and operate in Julia as if it was a simple CSV or a simple table without actually converting it into a data frame. And you have these other databases here like ODBC, MySQL, and so on in the Julia databases organization. So the second component, right? So we saw the first component of geospatial data, tables with measurements, and where these measurements are, right? So where these measurements are assigned to, that's the domain. So here in the right, I'm illustrating domain, which is a domain of the subsurface. This comes a lot in people working in geophysics or working in geological modeling in 3D, for example. Energy companies, mining companies, they do a lot of subsurface modeling. And if you see this here, it's very complicated domain, right? So you see this hexahedron geometries that are deformated, following these folds and all these horizon surfaces that are not very beautiful to represent in a computer, but the mesh can represent this. And so you take this physical region of interest and you break it down or split it down into these geometries, right? So each of these hexahedrons here is a place where you can assign measurements, right? So each of these hexahedrons corresponds to a row of the table we've seen in the previous slides, right? So we got this concept of domain formalized in the meshes.jl module, which is a submodule of a module that I'll be presenting tomorrow on geospatial data science. But this package basically formalizes all kinds of domains and structure meshes, grids, geometry sets, which are basically random geometries without any connection between the geometries. And you can easily look the code there if you want to learn more. It's a very, very general representation of domains there. So the most basic domain that I would like to start with is the one that's corresponding, for example, for you that are familiar with vector data, shapefile, and GeoJSON. How these data sets are usually represented, you have a soup of geometries. In geometric processing, we call this data structure the soup of geometries. Is an informal name for this. It's basically a collection of geometries that don't know anything about each other. You just say, give me a point, a segment, a triangle, a ball, put everything into a bag or a vector, and call this a geometry set. So that's the most simple representation you can get of a domain, right? So you have a region in space, you break it down into geometries and say, hey, this domain is made of a set of geometries. I don't know how they relate to each other, but they're here, right? And you put these geometries here into a vector, the geoms vector, and you wrap this vector into a geometry set domain. So that's how you create a geometry set with 4 geometries. these geometries live in a 2D space, that's why the 2 here, and they have coordinates of type float64, which is how you represent coordinates here in the machine. So as I mentioned, this is usually found in Shape, GeoJSON, all these formats that are used to save vector data. One of the most used ones, I think, that go beyond like a specific community, right? They are everywhere. Everyone doing computer science, doing geoscience, doing anything will come to somehow an array representation, which is just a structured set of dimensions with measurements. So that is the grid format. It comes up with different names in different communities, but it's raster, grid, structure, like so many different names. It's basically how do you represent images, how do you represent satellite images is the grid domain. And there are different, let's say, flavors of grids. The most easy one is the Cartesian grid that we call here. It's basically aligned with the coordinate axis, right? So if you have x and y perpendicular, you're just gonna count the x, y in regular spacing and count the y-axis in regular spacing, and then you're gonna build your cells. These are the Cartesian grid. So you only need to specify where the grid starts, the minimum point, where the grid ends, the maximum point, and the spacing. And you do this per dimension, right? So this structure can create 2D, 3D grids, ND grids without allocating any memory. And that's very convenient. I'll come back to this later, but basically this is a representation that is lazy. So it doesn't consume any memory, it just can represent grids of millions and millions of cells without any storage, basically, right? So that's the idea. And you usually find this in TIFF, GeoTIFF, right? Like raster, like netcdf, grid files. They are structured as grids. There are many flavors, and we have all these flavors implemented in meshes, and you can look it up. But basically, it's a very popular one that shows up in different domains, different scientific domains. What's the most general one? I think the font is super small, but I don't know if I can increase the slide font, but the most general one, I think, in the sense of representation, right? It can represent basically any of the previous domains, is the unstructured mesh domain, and it's a set of connected geometries, right? So basically, it's found in people working in physical simulation. A lot of people use VTK as the standard format for saving and loading geospatial results, right? So VTK is very famous. And people in computer graphics also use a lot of these other formats like STL, OBJ, object files, and mesh files, and all these other formats that are used to save geospatial data. So if you think of how you represent this, I will also have an example. It's basically like you only need to get this region in space. I don't know if it's easy to do this with one hand. So you take this region in space, so say I have a circle here, and you can just say, I'll take a specific set of points inside of the circle, save this into a vector of points. These are all the points that I'm wanting to use in my discretization. And I'll just give a rule that connects each of these points. So say point 1 with point 2 with point 3, make a triangle. Point 1, 2, 3, 4, 5, make a quadrangle. And then you can create all this list of connectivities. That's how we call. You get a set of vertices or points together with a list of connectivities, and you build your whole domain. So you have originally any shape you have, and you can discretize this shape into a set of geometries with a list of points and a list of connectivities, right? So that's what has, and that was I tried to show in the example. First, I build a vector of points that you can see there in the top, and then I build the vector of connectivities, right? So I don't know if it's easy to see there, but the vector of points you can create, for example, as a vector of tuples. You just say, here is a vector of 2D points with coordinates 0, 0, the other point is 1, 0, the other point is 0, 1, and so on. And the list of connectivities is this connectivity object also coming from matches that connects integers, right? So I'm saying, connect vertex 1, 2, 6, and 5 into a quadrangle. Vertex 2, 4, 6 into a triangle. And meshes will figure out by the number of vertices and the dimensionality of things how to connect this into actual geometry types, right? So if you feed this points and connectivities into a simple mesh, which is the explicit representation of the mesh, you get this domain data structure that has 6 vertices and 4 elements, right? So that's the general representation that can basically allows you to represent very complicated shapes in 3D and 2D and so on. So how do you actually get to the final point, geospatial data, right? So we have to combine tables with domains to get to the final representation, right? So that's the purpose of the single function called georef. So there's a function in the GeoTables package called georef that allows you to take any table that implements the tables.jl interface and any domain from meshes and combine this into a format that pretty much resembles a table, right? So if you look here at the bottom, it looks like a table, but it's a geospatial table, right? So in other languages, we've seen this concept before. It's nothing new. The novelty here is because we unified this for raster vector mesh. Anything fits in the same tabular representation, right? So other packages, maybe Python has, I don't know if it's rasterpy, pyraster. There's a bunch of other packages that do this for specific domains, right? So you have people working with, I think it's GeoPandas for vector data, right? And then there is a package, raster.io maybe, for Python that does the raster part. Here you have one single representation that loads anything, and it behaves like a table every time. There are many optimizations behind the scenes to make it work efficiently. For example, this geometry column here is never materialized. If you have a huge grid, you don't want to create a huge column of quadrangles or hexahedrons. It's just lazy. It looks like it's printing here quadrangles, but it's just like a few first 5 quadrangles or so, but it's never materialized. So this representation is explained in the Geospatial Data Science with Julia book. We wrote this book this year, and it's open access. I can share the link, but if you go online and search Geospatial Data Science with Julia, there will be a link to an open access book that you can read online. You don't need to download anything. It's just where these things are explained in much more detail. I'll be calling this book here GDSJL for short. So if you see GDSJL in the slides, it's because it's a reference to this book. You can see here one of the first things that I would like to point out in this representation is that it's aware of many useful things for data science. So the first thing it is aware of is the scientific type of the columns. So if you see here below the names of the columns, name, age, height, gender, and geometry, there is a subheader of scientific types. It recognizes that the column of strings is a categorical variable. The column of age is a continuous variable because I gave the units of years. This is a time unit. And the height is in meters, right? So it knows it's also a continuous variable. Male or female, the gender, it understands that it's categorical. And you see it in the third subheader that it has no units assigned. So this representation is very robust in the sense that it knows scientific types and it knows units.
Where did you get the units? As in, where did you input the units from?
It's very small, right, the font. So if you see here in the column, there's a U after the vector, so unit year.
So unitful.jl.
Unitful.jl, yeah. So there's a package in Julia, good question, Nathan. There's a package in Julia called unitful.jl. That's the package, one of the packages that supports units in Julia. So if you want to express your physical measurements with units, meters, I don't know, meter square, kilograms, the metric system, any units you can imagine, the unitful.jl package is the more mature package. There are alternative dynamic quantities.jl is another one that you can assign units to raw numbers, right? So we have integration with unitful so far. Unitful.jl is the one that is integrated in the ecosystem. And we can definitely add support for alternatives as well. So basically here you assign units, as Netino asked, the column here, age, I put the numbers, and I put the suffix here, U, Y, R, it means the units of year. And in the bottom here I say height, I give the numbers, and I say the units are meters, right? So it's very good to work with units. It's actually very good practice because you can catch a lot of bugs just by putting units there. So if you try to add inconsistent units, there will be a runtime error, or even sometimes maybe a compilation error when you try to do so. So you see like the table, this GeoTable here has the names of the columns, the scientific type, continuous, categorical, textual. There are a bunch of traits that are available in the data science traits.jl package. And it has the notion of units as well. That's very useful, and it tries to propagate these units in the geospatial data science stack as much as possible. Okay, so that's like the overview of what the GeoTable is. And you can see here also another useful information. The header here shows that that's a 4x5 GeoTable, 4 variables by 5 columns, right? Because the geometry column is considered a column, over a 2x2 Cartesian grid, right? So you see that the domain information is not lost. It knows that this is a grid, even though the geometry is showing as a set of random disconnected quadrangles. You still see that this is a Cartesian grid. So what are the benefits of a universal representation? Let me see how I am with time. Okay, what are the benefits of a universal representation? People from different communities can interact and work together. My goodness, how hard it is. We are 2024 and like climate people, earth science people, geoscience, they cannot talk to each other in software. They're just like doing their own stack, separating GIS from 3D modeling. It's just unbelievable. Like, I really hope that people can buy this message that we need a universal way of communicating between software stacks and communities. So consumers of this GeoTables representation can leverage an extensive ecosystem for geospatial data science, because GeoTables is one module of a much larger ecosystem. And this ecosystem is native Julia. It's written 100% in Julia. So if you go, I'll have a talk tomorrow that goes over a specific bit of this. It's one chapter of the book, but it's 100% Julia. So it's flexible, it's performant. There are corner cases, of course. We are working on the optimization of performance whenever it shows up, because we cannot handle all corner cases with a small team, right? But we make sure that it works correctly, and then we optimize for performance. So if you are curious about how these things work, if you want to contribute, you can just open. It's simple Julia code. There's no Fortran, there's no low-level pointers pointing to memory. It's like very high-level Julia code. More features to end users, right? So if you adopt something like this in your stack, so say I have a simulation solver, a physical solver that outputs GeoTables or consumes GeoTables with properties. Say you are working in the subsurface, you need to consume maps of permeability, maps of conductivity, maps of wind speed, whatever. If you consume this as GeoTable and you run your simulation and you produce a GeoTable, you can right away have a ton of features for you, like visualization of these tables is already implemented. You have all this geospatial data science stack for you. So if you need to do post-processing to clean data, manipulate it somehow, do aggregation, run a machine learning model, everything just works. You can just feed this GeoTable to the stack. It will just work all the way down. So it's very nice to be able to interact with this table after you have it constructed. And we will show here in this deck of slides as well that we have integration with all these file formats. So we support more than 20 file formats already. All these formats from GIS like Shape, GeoJSON, NetCDF through the backends. Alex is one of the maintainers of the NetCDF backend. So NetCDF, Grib, all these formats, VTK, they're all backends of this package called GeoIO that will load the data in the particular data structure that it loads and convert into a GeoTable for use, right? So if you care about just loading the data to get your work done in your scientific domain, right? So if you have a scientific question that you want to address and you don't want to waste time learning different underlying representations, you GeoIO it, get the GeoTable, and start working. And it is integrated with Maki. Simon is also here as the maintainer, one of the main maintainers of Maki, which allows you to do very high speed interactive 3D visualizations. We'll see some of this as well. So I don't know how much time we have for the live demo, but I will try. I have 10 minutes, so I'll just go example by example here. So here's how you see. I can share the script as well after the talk. I'm loading 3 packages in this example: meshes for the domains, GeoTables to take domains and tables into a GeoTable, and GeoIO to load these tables from disk in different formats, right? GeoMaki is the Maki backend for visualization. So you see some visualizations in this example here. So I can load these packages, right? So I'll just press Alt-Shift-Enter, and then I'll create my first geometry set here. I'll create a point, a segment, a triangle, a ball, and put everything into a geometry set. You see here in the right, the same example we saw. And then you can call this vis function, the vis g set. And this vis function here, my tablet is not very powerful. It will just open a plot where you can interact, you can zoom in, you can create boxes. It's just because I'm on here. You can create zoom, and that's basically like all that Maki has to offer, right? So if you create these 4 objects, there's a point here, there's a ball, there's a segment, there's a triangle. I can then visualize this geometry set with different colors, colors 1 through 4, right? So if I execute this one, you see that I have different colors for these geometries. I can then fix the data aspect, right? So by default, the data aspect is not the data aspect, right? So it's, you create this and you see that this ball is kind of an ellipse, right? In order to make it a ball, you have to change the aspect of the plot to be a data aspect. So if I execute this one, you see now that everything is in proportion, right? So the ball is an actual ball, and all these lengths are corrected, right? I can also add other things to this figure with the vis exclamation mark. So I can add the boundary of the ball in the color red. So if I execute this cell here, you see that the circle has a boundary in red. And I can also add the boundary of the triangle in blue, in black, right? So I can customize a lot of these details for the final visualization. So how the GeoTable works now? So here I created my domain, right? The geometry set for disconnected geometries. One thing I can do is just convert into a table that has no measurements. So I assign a nothing table. So I just say connect this nothing to the domain. That means I don't want to assign any measurements. So you see that it creates here on the right a GeoTable with just the geometry column, right? So the screen is not ideal, it's very small here, but you see that there's a geometry column and that's it. Or I can assign a table, right? So I can say here I'll create a table with a column A with integers 1 through 4 and a column B with random floats. And I will assign this table to the G set. If I do this, you see that, let me increase here. You see that, I will just execute like this. I think it's easier. You see that there are 3 columns now. A and B are features, are values. They have this pink color, and the geometry column is special. We color it green, right? So it's just to differentiate between what are columns of measurements and what is a special column of geometries. You see that it recognizes that integers are categorical and floats are continuous, right? So if you want to change the scientific type, you have ways of doing this, and we will explain some of this tomorrow. Let's come back here. So this GeoTable, as I mentioned, it's very clever sometimes with the ways you access the sub data sets, right? So if you say, I just want the first 2 rows, so I say 1 through 2, all columns, right? So if you do this, it will never materialize the domain, right? So if you had a huge raster, huge grid, it will just take a view into the grid and it will never create the subgrid because that allocates a lot of memory. But you see here that I have just the 2 first rows and the 2 first geometries, right? Point and segment. You can access the columns with the syntax geotable.column, right? It pretty much mimics what the dataframes.jl package does. And you have this other easy feature here, which is the viewer. You send a GeoTable to the viewer, and it will try to build a viewer for quick inspection, right? So if I say here, send the GeoTable to the viewer, you see that it creates this, let me zoom here. It creates this scene here where you can see all the variables that are in this data set. So there's variable A is categorical with 4 categories in the color bar. We need to use the new Maki's ecosystem for categorical color bars. And then if you change the column B here, it changes the color bar to a continuous color bar, right? So you see here different variables over this geospatial domain, and you can interact with the menu, you can zoom, you can do anything that Maki supports. Here is the grid domain. Let me see how much time. Okay, here's the grid domain. If you create a grid that's 5 by 5, you see here that it's represented like this, right? But if you visualize this grid, it's just a different domain, right? I can just give colors 1 through 25 because a 5 by 5 grid has 25 quadrangles, right? So if I just do this here, it creates this raster, right? So it's a set of 25 quadrangles, each of which has its own color, 1 through 5, starting here at the bottom left, ending here in the top right. I can also fix the aspect of this plot so that it looks like a square grid, right? Because now the coordinates are meshing in length here in the screen. And you see that this is a Cartesian grid with 5 by 5 quadrangles. It also works in 3D. You can just do it later with your own example. Here I'm calling this, and I'm asking for this option here, show facets. And show facets will just show the boundaries of each of this cell, right? So if I just say show boundaries, it will show these edges here, and I can also set the color of the edge if that's useful. So I'll just change the aspect again. I'll create here with color, and I'll pass facet color equals red. So if I change the facet color to red, it will show the facets in red now. It's very customizable, right? So we're trying to get more and more customization of this with the ultimate goal of having a unique set of aesthetics options that work with any domain. So that will facilitate you writing a script once and just loading in GeoTables over vector or raster, anything will just work the same. What else? I have here this other option, but I think it's more domain specific. If you feed to a grid of 5 by 5 quadrangles, a vector that's 36 long, that is 6 times 6. It's because you're assigning colors to the vertices instead of the quadrangles, right? So what it will do, it will call the Mackie function that does the interpolation in the graphics card, right? So it will just, let me actually do this here. It will look more smooth, and that's because I'm assigning colors to vertices and letting the graphics card do the interpolation, right? So it's sometimes useful to show this data like this because the fields you are mapping are usually continuous, right? So they're not just greedy-like visualizations, right? So that's an option that's also explained in the docstring, but it's more specific to specific type of workflow. Here I'll create another table. See, I'll create a table that contains the centroids of the grid. The centroids of the grid are just points, right? So I'll create this table here. And it knows that the centroids are these 2D points, and I can then georeference this table to the grid. And you see that it has the centroid as a column. So the columns can hold anything, basically, because Julia is dynamic, it supports this very high-level abstraction. It's not like pre-compiled to only support integer or float. It can support any type that you feed here as column. And in this case, the column of centroid is like a column of points. It shows as a tuple, but it's actually a point. But you can have any sort of measurement. So if you need to save vectors, matrices, or any tensor in your triangles of the mesh or in your raster file, you can. Here's the example of the mesh. I think it's the example in 3D. So I create a mesh, a sphere. You see it's a primitive, right? So I create a sphere with center and radius. And now I can do this discretization of the sphere into a mesh. So here's discretize the sphere with regular discretization, where the first dimension I want to 30 elements, and the second dimension I want 50 elements. And if you do this, it will create the mesh of the sphere, right? So you see here that this mesh has 1,500 vertices, and it has how many elements? Let me just write it down here again. It has 550 elements, right? Quadrangles and triangles. So I can visualize this mesh as well. Oh, sorry. I can visualize this mesh. Just go here. And it will show the mesh with the 3D Mackie scene, right? So if I can zoom here. This is a mesh of the sphere. You can zoom in, and you can imagine that sometimes you may be working on the whole Earth as a sphere or as an ellipsoid or something like this. You'll be able to flexibly visualize this and assign measurements to each of these quadrangles or each of these triangles here near the poles, right? So there are many options to highlight and color this. For example, I can assign this the area of each of these quadrangles on the sphere to this table, right? So what I did here, sorry, the code is so small. I created a GeoTable where I georef the area of each of these mesh elements. This dot here applies the area function to each of the elements of the mesh. and then assign it to the mesh itself. This creates the table. And if I send this GeoTable to the viewer, you'll see that the sphere has these elements that are colored now with their area, right? So the elements near the equator here have this, in this discretization, have this higher value compared to the area of these triangles here at the poles, right? Now the last bit, I'm on time. The last bit is the GeoIO module. So the GeoIO module has two functions, nothing more: load and save. Load any format. So here I'm loading a mesh in STL format. That's a format from the computer graphics community. And that will load the GeoTable, right? And I can just visualize the geometry column, right? So I can just visualize this geometry. Where is it here? And it will load this airplane model, right, that is available online. And so some people may be using geospatial data science not for Earth, for geoscience. They may be using it for engineering purposes, right? So if someone wants to load a mesh model of a plane, do physical simulations, and do some post-processing on the fields over the plane, how to do that? We facilitate this through this tech, right? So if you want to benefit from this, just adopt the GeoTables format. You get this for free, right? So now that I loaded the GeoTable from STL, I can save it as object, I can save it as off format, I can save it as mesh format, and these are different formats of unstructured meshes that are supported. I can also load a TIFF file, a GeoTIFF file here, right? So you see if I load it, let me increase here. Let me execute this here again. It has 3 variables, band 1, 2, and 3, and it has the geometry column. It's cut here from the screen, right? But you can do the same here. My tablet is not powerful, so it will take a bit more time here. So if I call the vis function on this GeoTable, it will perform the transformations that are stored in the GeoTIFF and show the GeoTable as a raster, right? Because if you see here at the top, this is a GeoTable over a transformed grid of that many quadrangles, right? So if you see here, it loaded this raster, this rotated raster, like it applied the transformation, and you can zoom in and do all your analysis as you usually do with other plotting frameworks, right? But
also select the planes?
Can you also what?
Select the planes? Oh, that's not the...
Oh yeah, so if you have multiple variables like here, band 1, 2, and 3, you can send it to the viewer. Let's see if it works here. Because they're categorical right now, right? So GeoTable has 3 columns. I can just send it to the viewer. It should be able to show the 3 of them with the menu as well. Let's see. The problem is that categorical, I should, before I send it to the viewer, I should actually reinterpret the categorical as continuous, right? So there's another transformation called coerce, that I should coerce band 1, 2, and 3 to be continuous in order so that it doesn't try to plot this variable as categorical. Because you see categorical color bars with thousands of categories will be like very ugly. It will show up soon. It's just taking time because it's a huge color bar with many categories. I should have converted these categorical columns to continuous first. So here it is. You see that, yeah, it's taking more time because it's trying to plot like thousands of categories, but it's a continuous variable saved as integer. I should coerce. So how you do this, we'll see more of this tomorrow. So I would say GeoTable and then coerce the columns, whatever, to a data science trait, so continuous. I'll show you more or less what it is tomorrow. It's not this specific code, it's almost like this. It will convert all these 3 categories to categorical variables to continuous so that you can plot it as a continuous field. And that's it basically. So that concludes the talk. I hope that you guys got the main message here, which is we are trying to really fight hard to this universal representation to benefit different interaction between different ecosystems and communities. And I think lots of it is already polished. We need some work on making some of these visualizations more efficient, maybe some help from the Maki team to call the right Maki functions with the GeoTable domains we have. But everything is very polished at this point, so I hope that you can just take a look at the book. I'll open it for the final here so that you have more things to see here at the end. So let's see. If you want to learn more, so that's the final slide. The book is the resource, I think that's the more organized one. So Google Geospatial Data Science with Julia, we call GDSJL. It's the book that has three parts. Part one is foundations. You'll find some of this there. There's part two on these queries and transforms. In part three, I think it's queries actually. And part four is applications. There are some chapters that are missing. We're still working on them, but most of the foundational work is already there. So if you read the book, you'll be very prepared to get used and start using this stack. You have the Zulip channel as well if you want to have more support after the conference. There's the geostats.jl support channel on Zulip. It's one of the platforms that the Julia community uses to interact. And if you want dedicated support, consulting services, just contact me. I can also help integrating some of this stack and working out specific issues. And tomorrow there will be another talk specifically on the geostats.jl stack, which is how do you take these GeoTables, process, visualize with more advanced transformations. That's it. Do you have questions? Yeah?
Yeah. First, thank you for the talk. It was really great. I look forward to trying it out. Do you also have coordinate reference systems? Is that part of the two things?
Yeah, so we are working, that's the plan for the next semester. We are planning to integrate coordinate reference systems in a better way. So far, we are not explicitly modeling coordinate systems, and I was also talking to Magda there. So we want to integrate more of the geodesy coordinate system work so that it's more smooth to end users. We don't want to ask end users to learn geodesy on all this complicated stuff, because most of the time the scientists just don't want to address the scientific question and not know what's the CRS of this table, the CRS of that, and everything crashes, so it's not compatible. We just want to hide this, and we need careful design for this. We're planning it for next semester.
You said that the GeoTables is able to read NetCDF as well. Does it include NetCDF does it also include NetCDF files that are not necessarily longitude, latitude based, but more like time and height based, for example, like dimensions that are not longitude, latitude?
Cool. So we are using Alex package on NC datasets and GRIB datasets to load these datasets as backend, right? So anything that the package supports, we support, but we also require what's the name of the convention? CF conventions? What's the?
Basically CF conventions,
So the
right?
assumption here, in order to load the table without any additional keywords that are specific to the dataset, we only support CF convention. You're saying, here's the GeoTable. If you want to use GeoIO directly and just provide the file name, adopt the CF conventions. If it's something that doesn't follow the convention where the variable names are well-defined or something like this, we just ask the users to go to the backend package that has more flexibility to load this in a different way and do the post-processing into a GeoTable manually.
All right, thank you.
Any questions? Alexander, vais atrás? Espera só um bocadinho.
Thank you. Thank you for the microphone. Thanks for the.
Hi, Alex.
Is this on? Thanks for the great talk. I was wondering, in your split, apply, combine engine that you use, do you use data frames under the hood, or do you have your own
macros?
engine?
Yeah. We developed our own macros in order to avoid the materialization of the geometry column, because that's expensive, right? So we have the group bys, transform, and combine. They do a clever job with the geometry column, basically. So they do the traditional split, apply, combine, avoiding materialization of the geometry.
Okay. And so, so you're not using data frames for this, right?
No.
And did you make some benchmarks to see? Because I think the data frame is really, really efficient.
Really,
so
really
I'm just wondering if you made some benchmark to see.
No, we didn't do any benchmark yet because, as I explained, it's like so much work to already get it working correctly, right? So we're focusing on making the stack work correctly, and then we will fix these performance issues as they come, because it's a small team, we don't have enough time to cover all the applications and use case. So usually, like, if someone finds a bottleneck, a performance bottleneck, just report it, we try to address or even contribute a PR. We are happy to review and merge.
Okay, great, thanks.